Okay, so in this lecture, we're going to implement logistic softmax train.py. Now, to put this script into perspective, so if you look in the course repo, you'll notice there's two files for logistic regression. There's logistic train.py and logistic softmax train.py. Okay, so logistic train.py was from my logistic regression course, which was the prerequisite to this course. So if you took that course, you would have implemented logistic regression for binary classification. Whereas if you're taking this course, you're learning about softmax for multi-class classification. Okay, so that's the difference. And feel free to look at that script as well if you want a little review of how that works. Okay, but for this course, we're going to only work on the multi-class case. Okay, so we'll start by importing numpy. Import numpy as np. And because we don't have process.py locally, we're also going to copy and paste that stuff as well. So we'll need pandas. So we'll import pandas as pd, and we'll need matplotlib as well. So import matplotlib.pyplot as plt. Okay, and so just to remind you, in the GitHub repo, there you'll see a from process import get data. So that's only if you have process.py in the local directory. And since we're in Colab, that's not the case. So I'm just going to copy and paste that stuff. Okay, so let's run this. Okay, so the next thing we're going to do is download the data set. So we'll just copy that from process.py. Okay, so that's the URL for the data set. Download the data. And we're also going to copy the get data function. And so here we have get data. Okay. Now for this script, there's going to be one important function we need, which is the y2 indicator. So y2 indicator. And this takes in some target vector y and the number of classes k. Although we could figure that out in the function if we wanted. Okay, so why do we need this? Well, as you recall, our targets are encoded as integers from 0 up to k-1. Okay, but in order to implement gradient descent, we need to have our targets one hot encoded. Okay, so you saw that in the theory lectures. So we'll begin by getting the number of data points, which we'll call n. That's the length of y. Then we'll create an empty indicator matrix. So this is np.zeros of size n by k. So n is the number of samples and k is the number of classes. Okay, and although you could do this more efficiently, we're just going to do it like this, the slow way, for I in range n, and we're going to just do one sample at a time. So we're going to say indicator matrix at a row I and column y of I. We're going to set that equal to 1. Okay, because y of I is only going to be, say, 0, 1, 2, or 3 if there are 4 classes. And so it's going to set the appropriate column to 1. Okay, and then once we're done that, we return our new matrix. Okay, so the next step is to just get the data. So we'll take this, paste that, and we'll say get data. Okay, so that loads in the data. And then we're going to assign a few important variables. So we'll get d, which is the number of columns in x. And we'll get k. So here's how we'll get the number of classes. So we're going to do the length of the set of y train, and we're going to OR it with y test. Okay, so how does that work? Well, let's just do a simple experiment. Okay, so suppose we do set of y train. What does that do? So this gives us all the unique values, because sets can only contain unique values in y train. And so it's the same thing with y test. So 0, 1, 2, 3, 0, 1, 2, 3. Now, so why do we do this or? So this is for the case where, let's say, some of the classes don't appear in the train set, or some of the classes don't appear in the test set. And so you would use the or to combine those sets together. Okay? I believe that's called a set union. I don't remember it. I'm not going to look it up right now. Okay, so just to demonstrate how that would work. So suppose you only have 0, 1, and 2 in the train set, and then you OR that with 2 and 3 in the test set. Okay, so what does that give us? Okay, so that gives us the set union. And yes, it's called union because the other one is intersection, which is, this is not. Okay, and so when we get the length of that set, we get the number of classes. Okay, and this is assuming the classes are encoded as 0, 1, 2, and so forth. Okay, so let's run that. Okay, so the next step is to use our y2 indicator function to convert our targets into indicator matrices. Okay, so convert to indicator. And we're going to say y train ind equal to y2 indicator. I'm going to pass in y train and k. And then we'll do the same thing for the test set. y2 indicator, y test k. Okay. And so the next step is to initialize random weights. So now we're initializing our model. So randomly initialize weights. And we'll say W is a matrix, rand n, so from the standard normal, and it's of size d by k. Okay, and then we'll create our bias vector, which is a bunch of zeros. You could also initialize it randomly. That's going to be of size k. Okay. And now we're going to define a few useful functions that will be used throughout this script. Okay, so we'll have the softmax. So we'll write this quickly since you've seen it before. So we're going to exponentiate the activation. And then we're going to divide by the row sum. So that's expa divided by expa.sum. Sum along the columns and keep dims equals true so that it broadcasts correctly. Okay. Okay, so now we have the forward function, which computes a prediction, or the output probability. Okay, so we have def forward. This takes an x, w, and b, and we're just doing our model computation. So it's softmax of x dot w plus b. Okay, so let's run this. Okay, and so the next step is to define the predict function. So this will take in p of y given x. Okay, so it takes in an n by k matrix with all these probabilities. It's going to return the argmax over the columns. Okay, so p of y given x over x is equals 1. Okay, so that's how we get our predictions. And then we have our metrics. So we have our classification rate. That takes in the targets and the predictions, and we return the mean. Mean of y equals p. Okay. Then we have the cross-entropy. So this is for the loss. So I call it a t in the script, but I'm going to call it y here since it's more consistent. And these are the output probabilities. So we'll just call that p of y for short form instead of p of y given x. Okay, and then we'll return so this is just the formula for the cross-entropy. So it's y times np.log of p of y given x. Okay, we could make this more numerically stable if we wanted, but this is fine for this script. Okay. So next we have our training loop. Okay, so we'll begin by initializing two empty lists to store the train costs and the test costs. By the way, remember that cost means the same thing as loss. So it's okay to call it cost or lost, whatever you feel like. And the point of this, as you recall, so just get used to this, is to plot the loss per iteration after we are done training. Okay, so that's always useful to look at so that you know that the training process completed successfully, that your loss converged, and that you aren't overfitting, and your learning rate is correct, and your number of epochs is correct, and so forth. Okay, so here I'm going to set the learning rate to 0.001. And, you know, because people always ask, how do you choose the learning rate? How do you choose the number of epochs? You just have to try and see what the results are. And if the results are not good, maybe your cost per iteration goes down too fast and doesn't converge, or goes down too slowly, then you have to modify your learning rate, the number of epochs, and so forth. Okay, so we're going to loop through 10,000 epochs. And then inside the loop, we're going to get our model outputs. Okay, so that's P, Y train. So these are not the predictions yet. These are just the probabilities. So this is forward, and we're going to pass in X train, W, and B. And then we have the test set, PY test, forward, X test, W, and B. And so the next step is to compute the costs for both the train and test sets. So we have C train. This is equal to the cross-entropy. And this takes in, so the cross-entropy function requires that you have one-hot encoded the targets. You could also not one-hot encode them and do this another way, but for this script, we'll do one-hot encoding. Okay, so it's Y train ind and PY train. And we do the same thing for the test set. So that's C test cross-entropy, Y test ind PY test. Okay, so now we have the cost for both the train and test sets. And so now we would like to add these costs to our list of costs. Okay, so we'll say train costs, costs, append C train, and test cost, append C test. Okay. And so now we can actually do the gradient descent step. Okay, so this is our gradient descent. And so again, this just uses the formula that we derived in the previous lectures. Now, something people always ask me is, well, can you put the equations that we're implementing in the code also in the lecture? So, you know, like a little pop-up of the equation. And so the answer is no, I'm not going to do that, because really, you should be coding this yourself, and you should be simulating that process of coding by yourself if you did not have me here. And so what would you do if you were coding this by yourself, which is the exercise for this course, by the way? Well, you wouldn't be waiting for the formula to pop up on the screen. You would make notes and then derive your code from those notes. Okay, so you want to simulate that process as closely as possible. So don't wait for the equations to show up on the screen. Take your own notes and use those notes. Okay, so we have W, which is minus equals. So that's the same thing as W equals W minus. And then we have the learning rate times the gradient. So what's the gradient? Again, use your notes. X train transpose dot, which is the same as matrix multiplication. And we have the probabilities, PY train minus Y train ind. Okay. And then we have our bias update. So we have learning rate times PY train minus Y train ind, and we're going to sum across axis equals 0. Okay. And just for our own curiosity, we're going to also print out the iteration number in the loss every 1,000 steps. Okay, so C train, C test. Okay, so that's our training loop. So let's run this. Okay, so that goes by pretty quickly. And so the next step is to print the classification rate for both the train and test set. And so notice you could have also collected these throughout the training process and then plotted those as well, but I decided not to do that. You can try it as an exercise. Okay, so we'll first get the train accuracy. So that's classification rate. And so this is computed based on the original targets, so not the indicator matrix. Then we're going to say predict py train. Okay, and then we're going to print final train classification rate. And we're going to print act train. And then we're going to do the same thing for the test set. So act test equals classification rate. We're going to pass in y test, and we're going to call the predict function on py test. And then we print that as well. So final test classification rate. I'm going to pass in act test. Okay, so let's run this. Okay, so this is the final result. We get 92% on the train set and 89% on the test set. Okay, and we'll see, by the way, if these results can be improved by using a neural network, so a nonlinear classifier. Okay, and just to make sure that our model converged, by the way, you could also use these numbers, but it's more difficult to look at a list of numbers than it is to look at a plot. Okay, so we will plt.plot the train costs, and we'll label that as well, train cost. And we have plt.plot test costs, and we'll label that as well, test cost, okay? And to get those labels to show up, we'll call plt.legend. And in the Python file, there's also plt.show, but because this is a notebook, we don't need that. Okay, so we could put it in, but it won't do anything. Okay, so let's run this. All right, and it looks like our model converges successfully. In fact, we probably could have stopped training earlier, but this is fine. Okay, so in this lecture, we're going to implement ANN-train.py. Okay, so just to recap what we've done so far. We began this project by looking at process.py, which was just to pre-process the data and get it ready for doing machine learning. Okay, then the second step was to learn how to make predictions. So we did predictions without any training. And so we saw that without any training, the model's just performing randomly, and it doesn't perform that well. Okay, and so after we did that, we then looked at logistic softmax train. Okay, so this was to use logistic regression with softmax, which allows us to use logistic regression with multiple categories. Okay, and this is in contrast to the prerequisite course where we looked at binary classification with regular logistic regression. Okay, and then in this lecture, we're going to look at ANN-train.py, which is kind of the final endpoint of where we wanted to get to. Okay, so we'll begin by importing NumPy. And we'll need pandas as well. And we'll need matplotlib. Okay, and just to reiterate, what we have in the Python script is from process import get data, but this only works if you have process.py in the local directory, which we currently do not. And we could put it there, but it's simpler just to do it this way since we're using a Colab notebook for the live lecture. Okay, so let's run this. Okay, so instead of importing process.py, we're just going to copy the important parts over. Okay, so here we're going to download the data set. And we're going to copy the get data function. Okay, so here's the get data function. Okay, and so from here we're going to define a new helpful function which we'll need for the training process. So it's y2 indicator. This takes in an integer encoded one-dimensional vector of targets and number of classes k. Okay, and this, remember, the point of this is to convert the targets into an indicator matrix, which is what is needed during the training process, because that is the form that we see in the equations. Okay, so in order to implement that equation, we need the one-hot encoded version of the targets. Okay, so we'll say n equals to the length of y, and we'll create an empty matrix of zeros. That's just to start, and p does zeros of size n by k. So number of samples by number of classes. Okay, and so the next step is to loop through all n samples. And for each sample, we're going to index our indicator matrix at row I, column yi. Okay, so why column yi? Well, so imagine you have 4 classes. So yi is either 0, 1, 2, or 3. That's going to tell us which column we want to set to 1. Okay, so we set that to 1, and since it's one-hot encoding, we only set one column to 1. And then we return the indicator matrix. Okay, so let's run this. Oh, and just a reminder, we could do this a faster way using the same method you saw in process.py, where we index using the range of n and then using the whole y at the same time, but I think this is more intuitive for now. Okay. So the next step is to get the data. Okay, so we'll get this, and we'll call getData. That gives us the data. And then we're going to define our shape sizes. Okay, so we have D. This is the number of columns in X. So xtrain.shape at index 1. And then to get the classes, we're going to do something that might look a little strange. So we'll say the length of the set of ytrain, and this is or set ytest. Okay, so what does that do? So the set, well, it's easier just to show you. So the set gives us a set, of course, of the unique values in ytrain. Okay, because sets can only contain unique items. So it does contain multiple zeros, multiple ones, multiple twos, and multiple threes, but because it's a set, we only get to keep 1, 0, 1, 1, 1, 2, and 1, 3. Okay, and why are we doing this weird pipe symbol? So this is kind of like an or in the world of sets, this is a set union. Okay, as opposed to a set intersection, which is not what we want. And so why are we doing the set union? Well, that joins the two sets together. So maybe, ytest contains a class that's not in ytrain or vice versa. Okay, so by doing both, we get all the labels that appeared in ytrain or ytest. Okay? So just to illustrate how that might work, it might be like 0, 1, 2 for the train set, but the test set only has 2, 3. Okay, but when we union those together, we get the whole thing, 0, 1, 2, 3. Okay, and then the length of this set is the number of classes. Okay, and then we have the number of hidden units, which is a hyperparameter which you get to choose by yourself. Okay, so you can tune this based on the results you see. And just as a reminder, because people always ask, well, what is like a rule of thumb? And my answer to that is there is none. Just try. Just try different values, see what works. That is the method. Okay, so let's run this. And the next step is to convert our targets into indicator matrices using the y2 indicator function from above. Okay, so we have ytrain ind. This is equal to y2 indicator, passing in ytrain and the number of classes k. And we do the same thing for the test set, y2 indicator, ytest k. And let's run this. Okay, so the next step is to initialize our neural network weights. So we're going to randomly initialize these weights. But the difference between this script and the last script is we're going to change the weights so that they become better. Okay, so we have W1. This is a sample from the standard normal of size D by M. Okay, so the number of inputs is D, and this goes to the hidden layer where there are M hidden units. And then we have B1, which is just going to be initialized to an array of zeros of size M. Then we have W2 and p.random.randn. This is of size M by K. And we have B2, which is another array of zeros of size K. Okay, so the next step is to define some useful functions. Okay, so these will be familiar if you've gone through the previous lectures. So we'll have the softmax of A. So you've seen this. This is so this takes the activation A and we exponentiate it to get expa. Okay, and then we divide the exponentiated value with its row sum. Okay, so the sum across axis equals 1, and we say keep dims equals true so that it broadcasts correctly. Okay, now let's run this as well. Okay, and we have the forward function, which is going to be slightly different. So this takes in the input x, the weights W1, B1, W2, and B2, and we're going to compute the hidden value first. So for this lecture, we'll use the tan h. We'll say tan h, but feel free to change that if you feel like. Then we have x dot W1 plus B1, and then we do the same computation on z. So we do softmax of z dot W2 plus B2. And so here's the difference. We're also going to return z in addition to the neural network output. And why do we want to return z? Because that's used in the gradient. Okay, so let's run this. And so now let's implement the predict function. Okay, so this takes in p of y given x, and we take the argmax and p.argmax over p of y given x over axis equals 1, so across the columns. So let's run this. Okay, so the next function we're going to create is for the classification rate. Okay, so this takes in the regular targets, so the non-1-hot encoded targets, and non-1-hot encoded predictions. So we return the mean of y equals p. So you've seen that before. Okay, and then we have the cross-entropy. Okay, this takes in the targets. So these are the 1-hot encoded targets, that we'll call it y. And the probabilities p of y. And from this we want cross-entropy. So this is the formula for the cross-entropy, which is the targets times the log of p of y given x. Okay. Okay, so now we're going to implement the training loop. So we'll start by creating a list to store our train costs. Then we have a list to store our test costs. We'll define the learning rate to be 0.001, and we'll go through 10,000 epochs. Okay, and again, how did I choose this? I chose it by running it and seeing if it worked. Okay, and so that's the kind of process you should go through. Try different values, check the loss per iteration after training, and then see if it looks nice. And if it doesn't look nice, then adjust your values accordingly. Okay, so we have py train and z train. So remember, forward now returns both of these things. Okay, so we have passing in x train, w1, b1, w2, b2. And we have py test and z test. So we probably won't use z test, but we'll assign it to a variable anyway. b1, w2, b2. Okay, and then we're going to basically follow the same pattern as you saw in the logistic softmax train.py script. Okay, so we're going to get the train cost, so that's the cross entropy, and we pass in y train ind, so the indicator matrix for y train, and py train, and we get c test, which is the cross entropy of y test ind py test. Okay, and now we have the costs, we can append them to our list of costs. Okay, so we have train costs dot append c train, then we have test costs dot append c test. Okay, and so really the next step is the centerpiece of this script. It's where we do our gradient descent. Okay, so W2 changes by learning rate times, and this is just the gradient from the theory lecture. So you should have your notes up while you're typing this, right? So again, simulate how you would do this in the real world, right? So for those who are asking, can you put the equations on the screen? Simulate how you would be coding this in the real world, where you would have the equations from notes you took, and you would be translating those from math into Python, right? It's not you copying this video or you watching this video straight through. We don't want to do that, okay? So we're going to dot ztrain transpose with py train minus y train ind, okay? So that's why we need to one-hot encode the targets, because otherwise we wouldn't be able to subtract them. And then we have B2. You know what? We'll do it this way. We'll say this is the gradient of W2, and this is the gradient of B2. So this is py train minus y train ind, and we sum across axis equals 0. Okay, and then we'll compute this intermediate quantity dz, which is equal to py train minus y train ind dot w2 transpose times, and this is the gradient for the tan h, z train times z train. So if you used a different activation function, then you would change this part. Okay, and then we have the gradient of W1, which is equal to x train transpose dot dz, and then we have the gradient of B1, which is dz summing across axis equals 0. Okay, so those are all the gradients, and now we can update the weights. So we have W2 minus equals learning rate times GW2. We have B2 minus equals learning rate times the gradient of B2. And we have W1 minus equals the learning rate times the gradient of W1. And then we have B1 minus equals the learning rate times the gradient of B1. Okay, so that's gradient descent. And then we can also, because this might take a while, we could print out the iteration number every few steps, every 1,000 steps. And we'll also plot the cost to make sure it's not, exploding or doing anything weird. All right, so let's run this. Okay, so as you can see, it's going pretty fast. It might be overfitting a bit as well. So we see the train cost is going up near the end. In any case, we can print the final classification accuracy. So we'll get the classification rate. We pass in y train and predict py train. So this would just be the last prediction made by our model in the training loop. You could, of course, use the model to get a new prediction, but this is good enough for our purposes, right? So we did do one extra step of gradient descent after computing this, but it's not that big of a deal. Or you know what? Let's just do it anyway. Let's just do it like this. Okay, so we'll get new predictions. So this is after training. We can ignore this and we can ignore this. Okay, so, and then accuracy test equals classification rate y test and predict py test. And then we'll just print those results. So final train classification rate, act train, and then we'll print final test classification rate, act test. All right, so let's run this. Okay, so we get 94% on the test set and 99.5% on the train set. So it's probably overfitting. But to get a better sense for that, we can plot the loss per iteration. So train costs, and the label is train cost. And then we'll plot the test costs, and the label is test cost. And we'll say plt.legend to show the legend. And let's run this. Okay, so as you can see, the test cost is going up around iteration 5,000 approximately. So one thing we could try is to rerun this. So as mentioned, right, this is the process. You try it, you see some kind of result you don't like, and then you change these hyperparameters and try again, right, until you get something that you do like. Okay, so we'll run from here since this is where we generate the randomly initialized weights. Okay, so run everything. Okay. So that's interesting. So even though the final test cost is lower than before, the actual test classification rate has gone down. Okay, so that's something to pay attention to as well. Just because the test cost is lower does not imply that the classification rate will be higher. In fact, one little experiment we could do is we could also plot the accuracies. So train accuracies, test accuracies. Okay, and then we'll just compute those in this loop. Okay, so act train equals classification rate. We pass in y train, and now we have to get the predictions. Predict py train, and act test equals classification rate y test predict py test, and then we append these to our lists. Train acts.append act train, test acts.append act test. Okay, and then when we are done, we can plot those as well. Okay, so train acts, I think that's what I called it. Yeah, okay, and then test acts act. Okay, so let's run everything again from here, and let's go back to 10,000 to see how the accuracy changes over time. Okay, so let's run this. All right, so the test cost has gone up, but what has happened to the accuracy? Okay, so despite the cost going up, the accuracy still managed to go up during most of that time. It did decrease a bit over here. Okay, that's just how these things go. Okay, so that demonstrates one thing that can happen that might be a little unexpected.
Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python, Part 1. In this lecture, we are going to do a few mini quizzes on training. Suppose that instead of doing multi-class classification, we do binary classification. So we use one node for the output, and we use a sigmoid instead of a softmax. What does the gradient update look like? Assume that we're using a one hidden layer neural network and we call the input to hidden weights W and the hidden to output weights V. Also assume that there are no bias terms. I'll give you a minute to think about it, or you can pause the video and come back when you have the answer. Please do not go to the next slide without trying it yourself first. The first step is we have to actually know what we want to calculate. This means we have to recognize that we want the binary cross-entropy cost function, and it means that we want the derivatives of the cost with respect to each component of V, which is a vector, and the derivatives of the cost with respect to each component of W, which is a matrix. We'll let Z sub Jn be the value at the hidden node for the jth hidden unit and the nth sample. The first step is to break things up according to the chain rule. This lets us calculate each derivative in parts. The next step is to substitute the actual expressions for the derivatives. The next step is to cancel out the tops and bottoms where we can. The next step is to multiply out the t terms and the y terms. And the final step is to simplify the expression. The next thing we want to do is calculate the input to hidden weight derivatives, which is a little more complicated. We can start again by writing out each partial derivative according to the chain rule so that we can do it in parts. The next step is to substitute the actual expressions for those derivatives. Notice how we can factor out some of the derivatives instead of writing the same thing out twice. And the last step is to multiply out and simplify the t's and y's again. Of course, we expect to get the same expression as before, y minus t, since backpropagation is recursive. This next quiz question involves using neural networks for regression instead of classification. The trick is to remember that a neural network for binary classification is just a bunch of nonlinear layers with a logistic regression layer at the end. So to do regression, all we need to do is keep the nonlinear layers, but put a linear regression layer at the end. In this way, the output prediction is not bounded between 0 and 1 and can take on any value. Keep in mind that to train this model properly, you also have to use the correct cost function for regression. Again, we'll be doing this for a one hidden layer neural network and ignoring bias terms, so there will only be one input to hidden matrix W and one hidden to output vector V. Take a minute to figure this out on your own, or pause the video and come back when you're done. But please do not go to the next slide without trying it yourself first. So if you recall, the correct cost function for regression is the squared error. I've written z out explicitly, so it's easier to take the derivatives. And so the next step should be pretty simple because it's the same derivatives as before, except we now don't have to deal with the sigmoid. One interesting thing about this is, if we drop the constant 2, which can be absorbed into the learning rate, this is the exact same update that we have for classification as well. Next, let's calculate the derivative of the cost with respect to the input to hidden weights. Note that because the only part that is changed when going from classification to regression is the output layer, then everything behind the hidden layer remains the same. We already showed that the update equation for the hidden to output weight is the same for regression as it is for binary classification. Because of this, the input to hidden weight updates will also be the same. Note that I've dropped the 2 here for convenience, since it can be absorbed into the learning rate. The last important thing to note here is that while these update equations are the same for binary classification and regression, that doesn't mean binary classification and regression are the same. This is because the y's and the t's represent different things in each update and can take on different values. Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python Part 1. In this lecture, we are going to summarize everything we learned in this section of the course. This section was all about how to train a neural network. Remember that the main two functions of any machine learning algorithm are train and predict. The first section was all about prediction, and the second section was all about training. We saw that the idea of training consisted of finding the best weights for the neural network. We defined the best weights as the weights that minimized our cost function. We saw that the idea of training consisted of finding the best weights for the neural network. We defined the best weights as the weights that minimized our cost function. We saw that our cost function is equivalent to the negative log likelihood of a categorical distribution. An example of a categorical distribution would be a die rule. We also saw that minimizing this cost function improves our prediction accuracy. In this section, we learned about backpropagation, which is just a fancy name for gradient descent in a neural network. You saw that while backpropagation looks really complicated, it can actually be done using only some basic rules from differential calculus. All that is required is patience and care. We saw how backpropagation is recursive, so it's just a matter of defining it recursively if you want to train a neural network with many hidden layers. Next, we followed our usual pattern of implementing code immediately after discussing theory. This is one of the main themes in all my courses. We do theory, and then we solidify it by writing code. It's always theory then code, theory then code. In particular, we used our simple two-dimensional dataset from the first section, which is just 3 blobs in a scatterplot. This example is very important because it allows us to visualize the dataset we're trying to classify. One important feature of this implementation was that it used vectorized NumPy operations, which made things go much faster. Next, we applied the training algorithm to the e-commerce dataset. Since we didn't get a chance to apply Softmax to logistic regression in my last course, since you only learned about Softmax in this course, we took this opportunity to implement that in this course. This also allowed us to compare the accuracy of the logistic model to the accuracy of the neural network model.